Hello, everyone. I'm Santhoshi Navallika from the University of Michigan Dearborn, and today I'll present a paper titled Context-Aware Sensor Fusion and Mode Switching Control for an Autonomous Underwater Vehicle, which is co-authored with the Professor Holweg. This work focuses on designing an adaptive underwater system that can sense, decide, and control itself based on the changing ocean conditions. As we know, the ocean remains one of the least explored environments on Earth. Autonomous underwater vehicles, or AUVs, have become essential for research, defense, and industrial inspection. However, underwater navigation faces challenges, which are the unreliable sensors in murky water, drift in the GPS denied zones, and unstable control leading to high energy use. To overcome this, there's a need for intelligent adaptive AUVs that are capable of adjusting their sensing and control strategies to dynamic ocean conditions. Around the world, institutions like MIT, NTNU, and NIOT are developing advanced AUV systems, which are focusing on endurance, adaptive path planning, and coastal mapping. Yet most of these systems still rely on fixed gain controllers and non-adaptive sensor configuration. Our work bridges this gap by integrating sensor morphing and control mode switching into a unified simulation framework for adaptive underwater autonomy. The primary objective of this work was to build a simulation framework for an AUV that can adapt both its senses and control behavior based on the environmental context. We designed a context-aware sensor fusion system using IMU, DVL, sonar, and camera data, coupled with a mode-switching control system that autonomously transitions between the cruise and maneuver modes, depending on depth, visibility, and the terrain. This was implemented in MATLAB Simulink and Simscape and validated through detailed underwater simulation studies. The overall AUV system was modeled in MATLAB Simulink and Simscape multibody, combining discrete time control with continuous physics. The architecture includes four main blocks: sensor fusion and estimation, position and velocity control, force and torque application, and mechanical dynamics. A central MATLAB function block continuously evaluates environmental parameters and triggers real-time switching between sensors and control modes. This modular design makes the model flexible and scalable for different mission profiles. The system is divided into five major subsystems. First, the sensor and estimation subsystem that includes IMU, DVL, sonar, and camera models fused through a Kalman filter. Second, position control that computes velocity set points from position error. Third, the velocity control converts velocity error into thrust commands with buoyancy compensation. The force and torque application block applies those control outputs to the mechanical model. Finally, the mechanical structure defines mass, inertia, and hydrodynamic drag using a Fusion 360 based AUV model. These components together form a closed loop adaptive system. The AUV was modeled with 6 degrees of freedom, simulating translation, rotation, and hydrodynamic effects such as drag, buoyancy, and external disturbances. The governing equations relate thrust and torque to the resulting linear and angular accelerations. This dynamic model captures realistic motion, including pitch, roll, and yaw, when the control forces act through the simscape environment. Now coming to the control strategy that uses a cascaded PID structure with two loops. The outer loop compares the desired and actual positions to compute velocity set points, while the inner loop regulates those velocities by generating thrust commands. Both loops include anti-windup and filtering for noise suppression. This approach ensures accurate trajectory tracking and stable performance across all three spatial axes. This diagram illustrates the overall architecture of the proposed AUV system. The AUV uses four key sensors: the camera, sonar, IMU, and DVL, which feed into the sensor morphing logic. Based on depth, visibility, and sensor health, the morphing block activates the most reliable sensor pair through the sensor selector. The selected data is processed by a Kalman filter, producing clean velocity estimates that drive the position and velocity PID controllers. The controllers compute the required thrust forces applied through the force and torque block to the Simscape AOV body. The transform sensor continuously monitors the vehicle's position and feeds it back to close the loop. This architecture unifies sensing, estimation, and control into a fully adaptive underwater simulation. Now coming to the sensor fusion and switching. The AUV uses multiple sensors, IMU, DVL, sonar, and camera, to perceive its environment. A Kalman filter fuses IMU and DVL data to produce reliable, noise-free velocity estimates. The sensor morphing logic then selects which sensors to trust based on the conditions, in which the conditions are: if there is a shallow and clear environment, then the camera and the IMU is activated. For the deep waters, it is sonar and DVL, or intermediate, it is IMU plus DVL. This ensures continuous and accurate navigation even under fluctuating visibility and depth. The control system operates in two autonomous modes: cruise and maneuver. In cruise mode, the PID gains are lower, favoring smooth and energy efficient motion. In maneuver mode, higher gains enable quick, precise turns near obstacles or steep terrain. Mode switching is triggered by terrain curvature, visibility drop, or sudden depth changes, providing an optimal balance between agility and efficiency. The simulation was run for 30 seconds using a fixed step solver with a time step of 0.01 seconds. The outer and inner PID gains were tuned empirically to 1.2, 0.5, 0.1, and 2, zero point 0.8, and zero point 0.2 respectively. Sonar grid resolution was set to 1.5 meters, camera range to 10 meters, and visibility threshold to 8 meters. These parameters enabled accurate evaluation of sensor switching and control stability under changing environmental conditions. Now comes the experimental scenarios and sensor behaviors. Two terrain scenarios were used for testing. The first was a rugged asymmetric seabed which forced frequent mode switching and aggressive control. The second was a smooth sinusoidal terrain representing stable open water cruising. IMU signals showed smooth acceleration. DVL data was noisy but stable after filtering. The camera captured clear patches in shallow regions, and sonar performed strongly at the greater depth. Together, these validated the adaptability of the sensor and control framework. Now comes the results and analysis. The AUV achieved stable, smooth motion across all three axes. The cascaded PID maintained precise trajectory tracking with less than 1.2-meter error and no overshoot during cruise and maneuver transitions. The Kalman filter converged rapidly, removing IMU drift and DVL noise. Filtered DVL signals yielded stable velocity feedback, and sonar camera fusion provided complementary terrain perception, sonar for depth contours, and camera for fine details. Overall, the system demonstrated robust estimation, adaptive sensing, and stable control under varying underwater conditions. These are the camera terrain patches and the sonar terrain patches in the two scenarios, respectively. In summary, this work presented a context-aware AUE framework that combines cascaded PID control, Kalman filter-based sensor fusion, and autonomous mode switching. The system achieved stable trajectory tracking, noise robust estimation, and energy efficient navigation across diverse terrains. Future work will include integration with ROS2 and UUV simulator for a hardware in the loop validation, development of adaptive gain learning, and 3D floor mapping using combined sonar and camera data. And this research was conducted under the supervision of Professor Holweg at the University of Michigan, Dearborn. Thank you for your attention. I appreciate the opportunity to share our work here at SEPOC 2025. Please feel free to reach out if you have any questions. Thank you.